Hello, welcome to the first video for Math 19661 1M1. I'm Sean Holman, the lecturer for the unit, and for the first 2 weeks of the class, the first 8 videos that we'll go through, we're going to be covering calculus, and this may be review for some people. If it's review for you, you can think of it as a warm-up to the new material that will come later. But we want to make sure that everyone is on the same at the same level as far as calculus, and so we're going to go over some of the basics of calculus. You may have seen this before, but here's the plan for the first 2 weeks worth of videos. We'll start out with differential calculus, going through methods of differential calculus and the basics of what derivatives are, and then we'll move on to integral calculus and the fundamental theorem of calculus, the connection between derivatives, integrals, and then there is one extra topic at the end you probably haven't seen before called Macaulay brackets, which is a little bit different, but we'll get to that probably next week. So calculus, what is calculus? So there's two basic operations in calculus. The first one that we're going to discuss is differentiation, or taking the derivative of a function. And so we imagine that we have a function of a variable x, and then we plot the graph of this function, y equals f of x. So this is an example here, showing a possible graph, but we couldn't have any function. And then the derivative of this function at a given point is the slope of the tangent line to the graph at that point. And so if we're at a given point x, then the tangent line, this line that just barely touches the graph at that point, is tangent, as we say at that point. And the slope, you should be familiar with the slope of a line, but this is the amount that it goes up or down divided by the amount it goes over in a given interval. And so the derivative of this function is defined to be the slope of the tangent line at the given point. And so in the beginning days of calculus, one of the big things was that we could figure out how to calculate these derivatives based on taking the limit of a sequence of secant lines, or slopes of secant lines. And so, for example, we have here the line that passes through 2 points on this graph. This is called a secant line that passes through 2 points on the graph. And so if we take the line that passes through x, and then x plus some small amount delta x, and this red line is the secant line, and then here we have the slope of the secant line. So this is the amount the line goes down, in this case, f of x plus delta x minus f of x, divided by the amount that it goes over horizontally. We call that the rise over the run oftentimes. And so this is the slope of that secant line for this given delta x. And we can then let delta x get smaller and smaller, so shrink that interval. So I show a few different examples here. Delta x gets smaller, x plus delta x gets closer to x, and you can see the slope of the red line is getting closer to the slope of the blue line. And as delta x gets infinitesimally small, very, very small, the slope of the red line will approach the slope of the blue line. And this is a way that we can take the derivative. See that the red and blue lines come together as delta x gets small. And so this formula here at the bottom of the slide is one way we can use to calculate the slope of the tangent line, which is the derivative. And so I'll do an example. As we move on, we're actually not going to use this formula in terms of the limit very often. We'll use a series of rules that we learn for calculating derivatives. But this is the basis of differential calculus, of taking derivatives, this formula. And I wanted to go over one example where we use this formula in red in order to calculate the derivative. And so suppose we have this function f of x equals x squared. The graph is then a parabola, and we want to calculate the derivative of this function. Well, I'll do this example, as I'll do most examples, by hand. And so we have the function f of x equals x squared. The graph is the parabola, something like this. And if we're at a given point x here, the derivative be the slope of this tangent line. So what we're looking at, we're at a given point x, then the tangent line to the parabola, we want to find the slope of that, and that's the derivative. And we're going to find it using the definition in terms of the limit. So this derivative, the notation is f with this little dash here. We call this prime, f prime x. And so definition, the limit as delta x goes to 0. So make delta x, shrink it as smaller and smaller, and the limit as it goes to 0, you get the slope of the tangent line of f of x plus delta x minus f of x divided by delta x. So these are the slopes of the secant lines through 2 points in the graph. So this is the general definition from the slide, and let's put in the particular function that we're trying to take the derivative of here, x squared. So f of x plus delta x is, first we have the limit, first limit. F of x plus delta x is x plus delta x squared minus f of x, that's x squared divided by delta x. And so you can use your algebra in order to expand this square binomial expression. So x plus delta x squared is x squared plus 2x times delta x plus delta x squared minus x squared divided by delta x. And now we simplify this expression, so we have x squared here, these cancel out, and then the delta x will cancel with this delta x here and here. Delta x squared goes away. So we then have the limit delta x goes to 0 of 2x plus delta x. And so now it's very easy to see what happens when you shrink the size of delta x. You make it go 0 to smaller and smaller. These are the slopes of the tangent lines, or sorry, the secant lines for the given size of interval delta x. Make delta x go to 0, and it just becomes 0, the delta x. So you get the derivative of 2x. The derivative is 2x. And so the derivative of x squared is 2x. Okay, so we can calculate the derivative in this way using this limit definition. But in fact, as I said, we're going to mostly use a series of rules for calculating derivatives that we're going to study over the next lecture or the next video or so. I do want to mention a few things about the notation for derivatives before getting on to those rules, though. The first thing is that this notation that I just used for the derivative of a function with the dash or prime is derivative notation that goes back to Isaac Newton. So we call it the Newton notation for the derivative. We're also going to use a different notation. It's very commonly used. And it is sort of justified by the limit definition of the derivative. So if we define this delta f to be the change in the function f given by the change in x from x to delta x, then this limit definition of the derivative is the limit as delta x goes to 0 of delta f divided by delta x. So change in f divided by the change in x. And this suggests a different notation, which is very commonly used. The derivative of f, df divided by dx. You think of this as one function here, df dx, and it just means the same thing as this notation with the prime, the derivative of f. It's a function, and at every point gives the slope of the tangent line to the original function f. And this second notation is due to Leibniz, who discovered calculus at the same time as Newton. And we'll use both of the notations. As it turns out, in some cases, one of them is a little bit nicer to use, and so you switch back and forth, use them equivalently, depending on which one explains the concepts better. Okay, so yes, we'll use both of these, and they just mean the same thing. Okay, and so here's a table of the derivatives, and you can calculate these derivatives by using the limit definition that we went over. And so when we actually calculate derivatives in practice, we'll use this table and also a few other rules that are going to be covered in the next video. And we do expect that you know these, so you should know all the formulas in this table. So the derivative of x raised to the nth power is n times x to the n minus 1. So we did x squared in the example. X squared has derivative 2x, one particular case of this first formula. Also, if you have a function which is constant, you can think of that as being x to the 0, and you get 0 here. But the derivative of a constant, 0. Think of this as just being the slope line, the tangent line of a function which is constant, going to always be 0. The derivative of the function e to the x is e to the x. The derivatives of the trig functions, derivative of sine is cosine, derivative of cosine is negative sine. And then the derivative of natural log of the modulus of x is 1 over x. So we do expect that you know these. You should just have memorized this formula or this table. And then in addition to these formulas from the previous slide, there are a series of rules that you can use in order to calculate the derivatives of much more complicated functions that are formed by adding or multiplying the previous ones together or taking compositions of those functions. And these rules that we'll be going over in the next video are the product rule, the quotient rule, and the chain rule. The product rule is for calculating the derivative of a product of two functions. And the quotient rule similarly is for calculating the derivative of the quotient of two functions when you divide them. And the chain rule is for calculating the derivative of a composition of two functions. These will be the topic for the next video. But this is the end of this one.